Hello, my name is Dervla Frumming with MIPI Alliance. Today's webinar is presented by Alain Egault and Simon Boussiard with Hardent. Both gentlemen are active participants with the MIPI Display Working Group. A few things to note before we get started. The presentation playback and recording and slides are available in the Knowledge Library at MIPI.org. The presentation is approximately 35 minutes and will then open up for a live Q&A session. Please type your questions directly into the Q&A panel and we'll try to get to as many as we can. You're currently viewing the webinar console and you can easily minimize or maximize each of these panels by clicking one time. Now I'd like to hand over to Peter Lefkin, MIPI Alliance's Managing Director. Thank you.
Thank you, Dervla. My name is Peter Lefkin, Managing Director of MIPI Alliance, and I just wanted to provide a brief update and overview of collaboration that we have with VESA, the Video Electronic Standards Association. MIPI and VESA have been liaisons and collaborating since 2013, and over that period of time, we've had a number of different projects that we've worked on with them, one of which will be the subject of today's presentation, the VESA Display Stream Compression DSC and Video Display Compression M, VDC-M, has been adopted into MIPI DSI-2, and that will be the bulk of the presentation for today. In addition to the collaboration on compression, MIPI has also worked with VESA with regard to MIPI's automotive SerDes solutions, and in particular, being able to include EDP and DP, embedded DisplayPort and DisplayPort displays, over APHI, MIPI's APHI long reach physical layer. And the development of an APHI protocol adaptation layer, PAL, for EDP and DP was issued this year. And so with that, our collaboration continues in the area of automotive and also continuing on a compression to ensure that DSI-2 remains in line with the compression standards from VESA. And we look forward to our continued collaboration. And with that, I'd like to hand it over to Alain and Simone from Hardent, who will give a presentation on leveraging video compression within MIPI DSI-2 for high performance displays. Thank you.
Welcome everyone. My name is Alain Egault and I'm VP IP Product at Hardent in Montreal. I'm also joined today by Simon Boussiard, who is Product Manager for our Video Compression IP portfolio. Hardent is a Canadian company based in Montreal that develops MIPI-compatible video compression IP cores and provide design services for the semiconductor market. Today, Simon and I will be introducing you to the video compression standards that are part of the MIPI DSI-2 specification, and we will be showing you how video compression can be used for mobile, AR/VR, automotive applications. First, let's take a look at display bandwidth usage for consumer electronic products. This logarithmic chart maps out the evolution of display bandwidth over time for various types of products that use display technologies, such as mobile, tablet, AR/VR products, and cars. Each dot that you see on the chart represents a specific product. When you compare this to the evolution of phi speed over the same period of time, what we can quickly observe is that the phi speed is not increasing anywhere near as fast as the display bandwidth requirement over time. Phi speed is increasing by approximately 20% per year, whereas display bandwidth has increased twice as fast at 40% per year, which creates a clear gap between the two. There are not too many ways to deal with this challenge. You either increase the number of transmission lanes in your design, or you lower the display bandwidth by adding compression. VESA, the Video Electronic Standards Association, recognized this need for an industry-wide video compression specification and standard that could bridge this gap. The first VESA video compression standard, VESA DSC, was released in 2015. The MIPI Alliance was the first organization to adopt the use of DSC inside its transport standard, MIPI DSI. VESA DSC has been widely adopted over the last 6 years, and it is now commonly used in many consumer electronic products. As display bandwidth requirement kept increasing, VESA identified the need for a second compression standard that would offer additional compression efficiency, and VDC-M, VESA Display Compression, was announced in 2018. Again, MIPI Alliance was the first organization to adopt VDC-M into its transport standard, MIPI DSI-2. We expect that DSC will coexist with VDC-M for several years to come. Since early 2021, VDC-M is starting to be found in some high-end application processor products. These are the ones that will require an additional level of compression to deal with the ever-increasing display bandwidth requirements. So let's take a closer look at these two compression codecs. The VESA DSC and VDC-M compression codec have a lot in common. First of all, both DSC and VDC-M are incorporated into the MIPI DSI-2 transport layer, which allows you to choose a codec depending on your bandwidth and power requirement. DSI-2 stands for Display Serial Interface. DSI has been conceived to be a high-speed serial interface between application processor and display module. It is compatible with both the MIPI D-PHY and C-PHY. Secondly, they have both been designed, the two codecs have been designed to have super small latency in the order of a microsecond, which is a key feature for serial market areas. Thirdly, they're both visually lossless codec. That means that the end user cannot distinguish between the uncompressed image and the compressed version. This has been proven through a series of rigorous tests conducted by VESA. Because of the wide range of applications where codecs are being used, the algorithm has been carefully designed to yield excellent picture quality for all types of content, natural images, video, text, graphic, or even complex enduring test patterns. In order to determine if DSC and VDC-M were visually lossless, VESA established a test methodology and a test plan. This methodology is based on a qualitative method. In this method, testers are shown two images side by side. One image is the original, and the other is an image that alternates between or flicker between the compressed and the uncompressed version. The tester are then being asked to identify which one of the two images is the original uncompressed one. If the compressed image shows no visible difference with the original, the tester will get it right 50% of the time. If there is a noticeable difference, the result will sway in one specific direction. This methodology is now documented into an ISO test procedure, the ISO 29170-2 procedures. VESA performed a series of tests that involved 30 testers who were shown a total of 250,000 images of various types, natural content, text, graphic, and test pattern, with 8-bit per component, 10-bit HDR, and so on. Basically, these tests have shown that with DSC at 8-bit per pixel, DSC is visually lossless. No one can see any noticeable difference for any of the different images they were shown. The same test methodology was then used later on for VDC-M. In this case, VDC-M have shown to be visually lossless at 6-bit per pixels. If you would like to find out more about VESA's image quality testing, a white paper and test results can be found on the VESA website. There is also an article by David Hoffman and Dale Stolitzka that describe in more detail the test methodology being used. So after hearing how DSC and VDC-M are both visually lossless, you may be asking yourself, which one should I choose for my application then? Essentially, choosing between DSC and VDC-M for your application depends on the interoperability requirements you have. and also the trade-off between the compression capabilities and the codec complexity, which depends on the encoding tools used by both codecs. VDC-M provides additional compression capability for the same or better picture quality as DSC. DSC compression allows you to target a compression factor of up to 3 or 3.75x, whereas VDC-M can let you aim at up to 5 or 6x. However, VDC-M is larger in terms of gate count and the RAM usage due to the more complex algorithm that it incorporates. The latency remains very low for both codecs. Basically, to summarize, you should use VDC-M for applications that target very high display bandwidth and DSC for other applications. There are many consumer applications on the market today that are already using DSC compression. We're talking about applications such as mobile, tablets, GPUs, AR, VR, automotive applications, and so on. So we can imagine that in the coming years, as bandwidth requirements continue to increase, the designer will also start to wanting to leverage even more compression with VDC-M. There are many benefits to using compression, and they depend on your application. In the case of mobile and mobile-influenced products such as AR, VR, we see market trends toward the use of multiple and foldable displays, ultra-high display resolution and pixel density, a shift to use HDR that brings content video from 8 to 10 bit, and an increase in the frame rate going from 60 to say 120 frames per second. There are many benefits to the use of compression: lowering your power consumption, smaller footprint, lowering cost, number of pins, and switching frequencies. For automotive applications, there is a clear increase in the number of displays inside cars and the number of image sensors too. So car makers are very sensitive to the cost and weight of the cable harness inside their car and will see compelling advantage to use compression to reduce the number of cables inside their car. So let's now take a more detailed look at the use of video compression in each of these markets, beginning with the mobile market. If you look at the mobile trend today, future high-end mobile will need to be XR ready and capable of gaming. And there's a big movement toward the use of OLED display, which has several repercussions. The use of ultra-high resolution pixel density, a shift toward the use of high dynamic range which require 10-bit video, and the increase in higher frame rate as mentioned earlier. So consequently, the DDIC frame buffer inside mobile have gone from 10 to over 100 megabit in size. So over the last 10 years, display bandwidth has increased by 23x fold, as we have seen in the graph at the beginning of this presentation, while display interface PHY only increased by about 5 times. And now with 5G phone, we brings even more EMI challenges, so future mobile products are only possible now with the use of visually lossless compression. Looking at this table, we can see the benefit of using compression on the number of file lanes required for various resolution and use cases. Compression allows you to use a smaller frame buffer and less transmission lanes that will result into less power consumption for your design. On the right-hand side of the table, in the red rectangles, you can see examples where the resolution, pixel depth, and frame rate are all increasing significantly. For example, for a VR application where you need 4K by 4K at 120 frames per second with 10 bit per component, it becomes clear that 5x compression offered by VDC-M becomes necessary. In the future, it's expected that DSC and VDC-M will coexist. The choice between using DSC and VDC-M will depend on the display resolution and frame rate required by your application. Essentially, the lower-end segments on the market with resolution lower than FHD does not require any kind of compression. The mid-range, with display resolution between FHD and 4K 60, will continue to use DSC. And the higher end segment of the market for applications such as 4K 120 frames per second and above will be based on VDC-M, which is what is starting to happen right now, as new application processors with VDC-M supports are coming now on the market. So let's have a look at the impact of using VDC-M decoder instead of DSC in the design of a mobile display driver IC, also known as a DDIC. We will focus on the frame buffer subsystem that comprise the video decoder, its static RAM, and the frame buffer. You can see the VDC-M frame buffer subsystem on the left side and its DSC-based equivalent on the right side. So what can you see here? Well, the decoder logic gates and static RAM are incrementally larger in the case of VDC-M compared to DSC due to the algorithmic complexity. However, the frame buffer size is significantly smaller for VDC-M than its DSC equivalent because of the 6 versus 8 BPP. As a final result, there is a 23% area saving by using VDC-M instead of DSC in this DDIC project. Imagine how large the frame buffer would be if you would try to make DDIC without even compression. The rectangle wouldn't even fit inside my slide. So as you can see, VDC-M offers an attractive design area saving when compared to DSC. Also, the power efficiency is really good. VDC-M explicit encoding is allowing to turning off the encoding tools automatically when not being used by the decoder, yielding power consumption approximately 75 to 80% of its DSC equivalent for same pixel throughput. There is also an additional saving that can be made by reducing the number of PHY lanes required. Now let's have a look at video compression for the XR market. AR/VR products are very demanding in terms of display bandwidth. Firstly, products require 2 displays, one for each eye. Due to the proximity and the large field of vision required to make the experience immersive, you need higher display resolution and higher pixel density. Higher frame rates are also needed to lower latency so that users don't feel sick. In the XR market, we can place products in 2 different categories. Tethered product, where the head-mounted display is connected over a cable, and wireless product that are self-contained, where there are even more challenges, such as power consumption and the physical size being so limited. So in the XR market, future product performance expectations are very significant. It's expected that resolution will hit 8K by 8K by 2025, which in turn requires refresh rate of 100 if not 200 Hz or 240 Hz and pixel resolution of 12 bit per component. So specification that highlight once again the need for increased level of compression like VDC-M offers. As you will see in this example, video compression can be applied to many blocks within an AR head-mounted display, such as the captures subsystem, the processor or GPU, the display interface output, and even the DDIC on the display module. So the use of DSC and VDC-M in XR product provide many benefits that include reducing the memory, buffer size, and bandwidth, which leads to smaller footprint, smaller cost, significant power saving, while keeping extremely low latency, which is also very important. So now, at this stage, let me hand over now to Simon Bussière, who will talk to you about video compression for the automotive market.
Thank you, Alain. The automotive market is definitely an interesting topic. There is a rapid transformation happening right now in this market, and the digital car has become an important focus for MIPI over the last couple of years. What is, like we see in this slide, the driver instrument cluster display, a center console display, and even a co-driver display or common car features. At the right of the slide, the table shows the next generation of display sizes and resolutions that we expect to see in the next 2 years. See how large these new displays are becoming, and naturally the display resolutions will also increase to maintain good pixel density. The key takeaway here is the obvious increase in the total visual display bandwidth inside cars. Of course, this display all need to meet strict electromagnetic compatibility requirements to reduce interference with the in-vehicle Wi-Fi and 5G communications. There is also the need to reduce the power to ensure the longest possible distance on a single battery charge. All this while maintaining functional safety and data integrity. This slide shows that new cars often have rear seat displays, usually offered to entertain passengers. They require ability to play real-time high-quality video. Also in some new cars, the rear view mirror has been replaced by a display connected to a rear camera. Replacing the traditional rear view mirror by a display system has many advantages. It can provide a wider viewing angle. The rear view cannot be obstructed by the passengers or any object carried in the vehicle. In addition, safety critical information, such as the distance with the vehicles behinds or obstacle behinds, can be added as an overlay on the display. An important point is illustrated in this slide. Displays are not necessarily close to an ECU mounted in a dashboard and often require longer cabling solution to reach the rear of the vehicle. Another very exciting car improvement that is getting introduced right now is the use of digital side mirrors. Traditional external glass mirrors are replaced by internal displays connected to external low-profile cameras. There are benefits of such approach. Nighttime poor weather visibility is increased by using advanced sensor and wide field of view optics. Internal mirror displays enable instant zooming and customizable driver display positioning that is unaffected by weather. ADAS features such as lane departure, blind spot, and backup assist symbology can also be supported. Given that the driver relies on the information displayed to make decisions, safety-critical displays in the car must be free of failure. When a failure occurs, it must be detected. In the next section, I will talk more about this aspect and specifically address the use case of such displays that use video compression. So what we saw in the previous slide is that more and more displays are being added to cars. But the question is now, how do we drive all these displays? What might come to mind first is, let's add more cables. But for car makers, the amount of cable is a big deal. Cables are the third most expensive component and the third most heaviest component after the chassis and the engine inside cars. So car makers are willing to spend extra money on cutting-edge semiconductors to avoid the use of expensive and heavy cables. With the proper architecture, it is possible to reduce significantly the number of cables inside a car. First, by building a car video infrastructure that leverages the newly introduced MIPI Automotive SerDes solutions, MAS, that I will briefly explain in the next slide. One important characteristic of MAS architecture is that it allows daisy chaining, which alleviates the burden of cabling all displays directly to the main automotive ECU. On top of that, video compression is definitely the most important feature that an optimized car cabling architecture can use. Essentially, having an architecture where every source and sync device are equipped with compatible video encoders and decoders will reduce the need to use more cables, which reduce the cost, and solve the MI challenge, as each cable will be operated at a lower bandwidth. One other important benefit is that compression can enable higher quality displays by allowing HDR content to be carried with no more bandwidth than standard dynamic range content. So what is MAS? MIPI Automotive SerDes solution combines a new automotive grade PHY called EPHY with enhanced low power, low MIPI DSI-2 display and CSI-2 camera protocols. When used together, MAS provide an end-to-end solution capable of functional safety, security, and data integrity across an automotive-grade serial link. There are MIPI adaptation layer specifications that define how existing MIPI protocols are encapsulated for efficient EPHY packet framing. As DSC and VDC-M video compression are adopted in MIPI DSI-2, MAS support them natively. This slide illustrates MAS applied to the digital side mirrors example. The digital side mirror display is a great application for MAS because it requires that camera sensor, ECU, and display work together as an end-to-end system to ensure functional safety and pixel data integrity. As explained in the previous slides, DSC and VDC-M, which are visually lossless, low footprint, and low latency compression methods, are natively supported in MAS. MIPI promotes the use of video compression to mitigate the increasing number of displays and their higher resolutions. Note also that EPHY provides an excellent packet error rate that is better than 10-19, which will allow the use of video compression without concern of getting corruption on displays. Given that car manufacturers are very sensitive to image quality, and that MIPI is the first standard body to adopt and promote the use of VDC-M compression, MIPI recently released a white paper about a study done to validate the use of VDC-M compression for automotive displays. The study includes subjective trials to demonstrate that VDC-M image quality performance at the most aggressive 6x compression ratio meets the criteria required to be recognized as visually lossless. If you are interested, you can download the white paper from the MIPI website. So now let's see what bandwidth can be saved by VDC-M. Here we have a table that summarizes the pixel bandwidth analysis for 7 different display configurations. For example, trim levels of a car model. Each row calculates the display bandwidth requirements for a daisy chain topology. On the left of the table are the display parameters, and on the right, the total bandwidth required for all displays together. Let's focus on the total bandwidth section on the right. The calculations highlighted in red indicate the total uncompressed data rates for each of the 7 levels for both 8-bit per component displays or 10-bit capable displays. Now, if we look at the 2 last columns of the table, we can see that these data rates can be reduced drastically using VDC-M compression at 6x ratio. This allows the design to reduce the required number of file lanes and/or link rate. In summary, the benefit of reduced bandwidth using VDC-M compression is also a reduction in power, improved ANC, and cost reduction through interface savings. Now, you might be asking yourself, is it safe to use video compression for automotive displays? Will the addition of compression, decompression engines prevent from meeting the functional safety requirements that are mandatory for advanced driving assistance systems? Let's take a look and see. As seen in the previous section, many displays in cars provide information to the driver that is safety critical. For instance, the instrument cluster display will show icons called telltales to indicate a problem with the engine, or the braking system, or even with the assisted or autonomous driving system. It is then imperative that the pixel integrity be guaranteed even when the display leverages video compression. The same goes for the center console that will stream the video from the backup camera. It must display all video frames correctly and avoid freeze frames, otherwise consequences could be serious. Fortunately, automotive industry standards such as ISO 26262, the Functional Safety for Road Vehicles standard, exist to guide automotive electronic manufacturers on including functional safety features and how to show proof they are working. I will provide more details on the principle behind this standard in a coming slide. It all starts with the definition of safety goals. You will find it strange, but there is no clear definition of what a display failure is, and what is acceptable for one display could not be acceptable for the others. Regardless of whether compression is used or not, different automotive IC makers could give different answers to the question on that slide. A common answer to all this question is, it depends. It depends on what the main purpose of the display is. Nonetheless, for displays that contain safety critical information, there are no compromises, and having a mean to detect any pixel corruption is what automotive AC makers are aiming for. Here is a brief summary of the functional safety assessment process based on ISO 26262. The complete process is way more complex than we have time to show in this webinar, but for the sake of simplicity, here are the key steps that come after the safety goals have been determined. First, failure modes and their effects are identified. We then try to select diagnostic mechanisms that we want to implement to detect these failures. Diagnostic performance, fault coverage score in percentage, must be determined for various types of hardware faults: single point faults, transient faults, and latent faults. A thorough process called FMEDA, failure mode effects and diagnostic analysis, is achieved to get final metrics. Required performance depends on ASIL levels, that themselves depends on the severity, the exposure, and the controllability of the failure event. Part of MIPI developed a new specification called Display Service Extension. DSE is a protocol that adds functional safety features, as well as security and authentication features, to the end-to-end solution. DSI-2 packets are encapsulated in SEP, Service Extension Packets. For automotive displays, DSE functional safety feature protects display stream packets and their payload, so the pixels, during the transport over AFI. The main mechanisms are CRCs and message counters to ensure all packets are received and their integrity is correct. By using these diagnostics, fault can be detected easily on the display side and reported to the host. One concern that could be raised by automotive IC makers when using video compression is that DSE protects the compressed pixel, but not the actual image pixels. A decompression step using a decoder is required in the display to recover the pixels. Failure may occur during that decoding process, and detecting these faults is quite challenging. Common techniques would be to duplicate the decoder and compare both instance results. The solution is expensive. An important consideration also is that the decoded image is actually not identical to the original image that was presented to the encoder input. DSE and VDC-M are visually lossless, but not mathematically lossless, which means it is expected that pixel will have been slightly modified. So how can we solve this problem? Here's the trick, and it's simple. DSE and VDC-M algorithms are based on a pixel prediction loop, and such a compression step is replicated in both the encoder and the decoder. What does it mean? It means that during the encoding process, a compliant DSE or VDC-M encoder will have to generate the reconstructed image, the decoded image, in order to generate the next predicted pixel. In other words, a free copy of the decoded image, the exact same image that will be generated later by the decoder in the display, is available during the encoding process. We will then leverage that to build a very efficient diagnostic tool that will be described in the next slide. Given the decoded image also exists on the host side, we can simply compute CRCs of the decoded image and transmit those expected CRCs to the display. On the display side, once the decoded image is regenerated by the DSE or VDC-M decoder, the same CRCs are generated locally and compared to the expected CRCs received from the host. This diagnostic tool becomes a higher level, end-to-end powerful functional safety feature. The decoding process becomes fully covered. At Arden, we have developed this solution for many automotive IC makers, and it allowed them to safely use video compression. There are many benefits to using this approach based on the decoded image CRCs. The solution is low footprint, CRCs are easy to implement. It provides very high safety goals violation coverage for single point faults and transient faults. Coverage is end-to-end, including decoding process. If required, a CRC per slice region can be generated to enhance the granularity of display failure detection. Note that MIPI has expressed interest in standardizing this solution, and it could be part of a future DSC spec revision. Given this solution, we believe that it is then possible to meet functional safety requirements when using DSC or VDC-M compression. This concludes our look at the automotive market, and I'll now let Alain continue with a short summary.
Thank you, Simon. Let's take a look at some of the takeaways from the webinar. Video compression is essential for meeting the bandwidth requirement of current and future display application. VESA DSC and VDC-M offer proven compatibility with the MIPI DSI-2 interface and visually lossless performance. Integrating video compression into a design and achieving desired display feature can be complex. So IP and IP subsystem solutions are available in the market today to help designers lower risk and achieve faster integration. We hope that you enjoy our presentation, and we look forward to taking your questions now. I'll now be handing over to Jan from MIPI for the Q&A session. Thank you.
Yes, hello everyone. My name is Ian Smith from MIPI Alliance, and I'm here to help with today's Q&A session. If you have questions, please submit them now using the Q&A dialog box, and we look forward to answering as many of your questions as we possibly can in the next 20 minutes or so. I'd like to thank Alain and Simon for this excellent presentation. I certainly learned a lot from today's presentation. So thank you for all the effort, hard work that's gone into producing today's webinar. So let's get stuck into some questions.
Sure. Thank you, Jan.
Yeah, thank you.
Okay, first question up. Is it possible to use DSC to compress RGB data for sub-pixel rendered display for OLED panels? Who would like to take this one? I think perhaps this one is for Alain.
Actually, going to be Simon in that case, right, Simon?
Yeah, I can take that question. Yes. Actually, yes, it's a good question. We get that request very often from our customer, actually, and let's explain the reason why we would like to compress sub-pixel render stream. We talk about a case where the sub-pixel rendering function is achieved in the OS, the application processor, instead of a display driver IC. There are various reasons to do that, but one of them obviously is reduce the number of samples you want to transmit over a MIPI link. And naturally, applying DSC compression, you get a further bandwidth reduction. So you're interested to use DSC on such a stream. So the answer to the question, in fact, is yes. DSC can be used for that use case, even if DSC standard doesn't have a native encoding mode specific for RGB or any sub-pixel render structure color space. There is a YCBCR 422 mode, which involves a similar subsample pixel arrangement compared to those streams, so it can be used. For instance, you can simply map the G components into the Y component and the R and the B components into the CBCR components. So that's one trick that is being applied a lot in the industry, in fact.
Okay, thanks so much for that comprehensive answer.
Welcome.
Let's move on. Next question. We've got quite a few questions coming in now, which is great, but please keep them coming. Next question's up on the screen now. You said that VESA rated VDC-M as visually lossless at 6 per pixel. Are there use cases where a lower bit rate could be used?
Yeah, thank you, Jan. So it's a good question. So let me give a bit of background. So obviously DSC was first invented, and some visually lossless tests were performed on DSC. And we have come to the conclusion that DSC can be perceived as visually lossless with 8 BPP or 8 bit per pixel compression factor. So when VDC-M was following its creation was launched, we've conducted the same test and initially demonstrated that VDC-M is equally or superior to DSC picture quality with 6 BPP, so a benefit of 33% additional compression. But in theory, actually, you can drive VDC-M down to up to 4 BPP. And so we started running tests at lower bit rate than 6 BPP and try to identify if for some use cases, VDC-M could be perceived as visually lossless. And we came to the conclusion that the answer is yes. So in fact, MIPI published a white paper about some of those tests were done for the use case of automotive application. We've created the specific type of graphic elements you find inside a car, things like instrumentation and navigation panel and so on. And we were able to demonstrate that lower bit rate, like 5 BPP, that you can actually achieve visually lossless picture quality. The reason being that, the specific cases of graphic or complexity or maybe less than some other cases, and also the distance with the viewer and the intensity by which you're looking at images varies from application to other. So definitely VDC-M can be used at lower bit rate like 5 BPP.
Excellent, Alain. Thank you. Obviously, great flexibility there in terms of what the codec can support. Let's move on. We've got lots of questions in the pipeline here. Let me get the next one on the screen. So what is the cost? We always get a question about cost. What is the cost, gate count / RAM to implement VDC-M compression for FHD? Same question for decompression. Alain, Simon, would you like to, who would like to lead on that one?
Well, I can start with that one and maybe let Simon involved. So first off, sure. I would say that, VDC-M has been designed for higher throughput type of application. So FHD, assuming we're talking about 60 frames per second, is a fairly low bandwidth. And typically you'd find probably make more sense to use DSC. VDC-M costs additional gate because of its additional complexity. So I think it's fair to start to look at VDC-M for application that exceed, like the gigabit per pixel type application. So to answer the question, on the compression side, the complexity is, approximately 2x the one of DSC for similar pixel throughput, but it typically is used in application where DSC would just require many hard slices, probably too many hard slices for to make a possible application. On the decompression side, it is slightly larger than the other decoder, the DSC one, but you also have to look at the benefits. Obviously, quite often people have a frame buffer in the DDIC, for example, and because of the additional compression, the frame buffer will be substantially smaller in the case of VDC-M, where you'd use maybe 6 BPP instead of 8. So the estimates we've made is that in a typical DDIC, for the frame buffer subsystem, you actually have about a 25% saving using VDC-M over DSC. So that's effectively what ended up happening. You want to add additional color to this, Simon?
Yeah, sure. I mean, obviously it depends on the implementation of each implementation, but it's not a linear comparison between DSC and VDC-M. Sometimes for some specific use case, DSC could be slightly larger because, you know, for instance, the decoder is implementation is at 3 pixels per clock, whereas VDC-M is 4 pixels per clock. So it really depends the achievable operating frequency versus what you were trying to meet. So it's case by case, but generally, on average, VDC-M will be smaller on the decoder side. That's what we have seen in our analysis.
Okay, thank you for that response. I think I have a similar question. I'll put it up on the screen just to see if we can derive any more from this question. What is VDC-M RAM and decoder logic difference, ballpark number, compared with DSC? I think we just covered that, guys. Is there anything else in this question that you see?
Yeah, so again, I think it's case by case, and it's probably better to work with a given specific case and do the analysis to get the thorough comparison here, because it's hard to come up with the exact answer.
Okay, I mean, so yeah, it's obviously difficult to give generic answers sometimes. Obviously, if you do want to, you know, it's a question for the audience, if you do want additional information, then obviously you can reach out to us through the admin at MIPI.org email address with more specific questions, and we can connect you to our experts today if you need to get more information. Okay, so let's move forward. Push the next one to the screen. Again, comparing DSC and VDC-M, how much does the power consumption differ for the 1/3, 1/4 compression cases? Would you like to lead,
want to go ahead, or I can answer if you want to. No worries.
Sure.
Yeah, so definitely for VDC-M, one advantage is that the encoding tool, as Alain explained in the presentation, are explicitly signal in the encoded bit stream, which make, in fact, the task easier for the decoder in terms of reconstructing the pixel, because it doesn't have to rerun all the same tool as the encoder to implicitly determine what was the decision in each encoding mode. So definitely the power is reduced on the decoder side because of that. Many gates are in fact gated. Most of the logic is not operated whenever a specific encoding mode is signal in the bit stream. So when doing some more thorough analysis, we clearly see that VDC-M has an advantage in the power reduction for the display driver IC.
Okay,
maybe to add a little bit of color. Yeah, maybe to add a little bit of color to that too is, like, obviously when we're looking at power, we need to look at not only the codec but the entire subsystem system. You know, when you have the codec VDC-M as this explicit encoding, which allow to do some saving, but you need to look at, you know, if you reduce the frame buffer size, you save some power there, or you have less lanes or less PI to drive. So we've done actually a test case with DDIC for a 4K 120 frame application, and we compared apple to apple, so to speak, between a DSC DDIC and a VDC-M. And the conclusion was 80% of power consumption on the VDC-M compared to DSC. So about a 20% saving. But that's those cases, it's one particular case, but it's going to vary from case to cases.
I suspect a much more detailed analysis can be done if necessary, based on a more specific perhaps use case. Is that correct?
That's right, and that's quite typical. You know, when we engage with customers, we have to basically analyze the whole system to come to those kind of numbers, and it takes a detailed architecture analysis to come to some number and conclusion there, and it varies from system to system.
Okay, let's move on. I think we have a similar question here. Again, I'll push it to the slide here. Given the number of gates and VDC-M is more than DSC, I was wondering if there is a rough power data difference between the two compressions. Anything else to add based on this question?
I think pretty much what we just answered, I guess, on the previous question is the data that we can really share at this time. Yeah.
Okay. Okay, let's move on in that case. Next question related to latency. What about latency on compression? I think you put some figures in one of the slides, but perhaps you could just recap.
Sure. Well, essentially, you want to take it, Simon, or you?
Oh, yes, I can, definitely. So, I mean, both DSC and VDC-M are very, very low latency codecs. We're talking about a few video lines here. That's very low compared to you know, other codec for streaming usually. So, DSC and VDC-M, there's I mean, I would say a small difference. VDC-M takes, let's say, one additional video line on the encoding side and one additional video line on the decoding side compared to DSC. So we're talking about probably 5 video lines end-to-end in the case of VDC-M. Again, it depends on each use case, resolution, number of slides you're going to have in parallel, but roughly, let's say 5 video lines for VDC-M.
So speaking in terms of time, we're talking about a microsecond, like in this order of magnitude. So let's say, you know, a little bit less than a microsecond for a 4K application on DSC and maybe, you know, 2 microseconds for VDC-M. That's what we're talking about. So definitely not perceptible by humans.
Yeah, it's seamless.
Exactly.
Yeah. I'm guessing those kind of figures are kind of state of the art for any codec. Is that correct?
Yeah, absolutely. I mean, many other codec require full frame buffer or a significant part of a buffer and would end up with delays that are on the millisecond, which is like 1,000 times bigger than what we're talking about here. So that's pretty much cutting edge what we've got here.
Yeah. Okay, thank you, guys. So just a reminder, we've got a couple of questions left in the queue, but if there's anyone out there sitting on a question, please submit it as soon as possible so that we can cover it in the next 5 minutes or so. Okay, so let's move on. Next question we have. So for AR, VR applications, have there been any quality tests done in stereoscopic 3D mode? And if so, what were the results?
Yeah, it's a great question. I'll take that one. It's a great question. I mean, this question was done essentially by, you know, the VESA group asked themselves that question. It's like, you know, if we start to use our visually lossless codec in a stereoscopic application like AR, VR, what's going to happen? So basically, VESA gave a mandate to York University in Ontario, Canada, to conduct such a study. So York set up a stereoscopic test lab to perform those tests, and essentially selected a number of images And basically, we ran, the visual lossless test that we had initially run with mono views or single picture views were run equally on monocular as well as 3D stereoscopic images. And the result we ended up are maybe a bit counterintuitive, but we end up with the conclusion that viewing the same content in 3D has no impact or even a reduction of impact in terms of artifact detection. So clearly made the point that our VESA codec technology can definitely be used for stereoscopic 3D AR/VR application. Those results are published for VESA members on the VESA website. So I understand a number of people on this call or probably company with VESA membership. So just look up for York University stereoscopic 3D view. The tests were performed last November.
Okay, thank you, Alain. Let's move on. Last couple of questions here. Okay, so when there are errors in the DSC or VDC-M bitstream, does it affect all the pixels in the frame and all subsequent frames?
Yeah, I will take that question. That's a good question, and it's a normal concern that any IC maker can have when using compression, of course. So first, we need to remind people that both DSC and VDC-M are what we call intra-frame codecs. It means that there are no dependencies between encoded frames. So if a corruption occurs into one frame, it will affect only that frame and not the next frame. Obviously, it means a good decoder implementation will reset to a non-stain between frames. We assume that. Typically during the vertical blanking period, so it ensures that errors are not propagated from one frame to another frame. Second, even within each frame encoded, DSC and VDC-M operate on what we call slices, which are smaller region of an image. Each individual slice are again independent of each other. Slice size will depend on a variety of factors, but slice height, the number of lines per slice, is typically like 32 lines or something closer than this. So when an error occurs in a slice, only that slice is affected, and other slices in the image remain unaffected, so will not show any corruption. So, of course, the likelihood of getting a bitstream corruption and possibly a slice corruption depends on the transport layer bit error rate. And I want to remind people that in the case of automotive application built using the mass, which use the new A5, the bit error rate of 10 minus 19 is very low, and the compression, that's a corruption, the next extremely rare, unlikely event in that case. So that's my answer. Nope.
Might be muted, Jan.
My apologies, I was muted. So yeah, last question. If I were to use the decoded image CRC method that you showed in the automotive use case, how fast could I detect the failure that is happening? Simon, is this one for you?
Yes, definitely, since I covered the automotive section. Yes, again, it's a good question. So let's say we implement the CRC method that I described. So the short answer is within a frame period. In my presentation, I've described the general approach, but I didn't talk about how many CRCs per frame were to be implemented, what part of image each CRC will protect, and when CRCs are, ready and to be transmitted and verified on the other side in the display. This will be specified in the next DS specification revision. But let's consider a simple, solution implementation of this. The decoded image CRC, in fact, are computed in parallel at the same time of the active frame is encoded and transmitted, on the host side. And then on the display side, that CRC calculation also begins as soon as the first pixel come out of the DSC decoder. So regardless if CRC covers only a single slice, column, or the entire frame, we know that during the vertical blanking following the frame, between frame, the pause between frame, the final CRC values are obtained and stable. So a very simple approach is to transfer all the CRCs during the vertical blanking and perform the verification during that same period on the display. So if an error occurs at the early stage of a frame, the first pixel of a frame, as an example, it means the worst case fault detection latency would be 1 frame period. Usually this is acceptable because the system will have time to take action before the next frame begins.
Okay, Simon. Thank you for that response. I think that's taken us through all of the questions. I think the only other question I can see is regarding how you can get hold of a copy of the presentation. That should be available actually already in the resources window. But rest assured that after this webinar today, both the recording of the whole session will be made available on demand, as well as all the resources such as the slide deck and other related documents, webinars, etc. will be made available. So in terms of just closing remarks, Alain, would you like to just add any other last words?
Sure. I mean, I'd like to thank everyone who attended the presentation today. We appreciate your interest and, at the hard end, and we look forward for any subsequent question you may have. You can reach out to us through MIPI or directly, and we'd be delighted to discuss some more about our compression technology. And I'd like to thank the folk at MIPI who provided us the opportunity to present our technology today. Thank you all.
Yeah, thank you all.
Thanks, Alain. And yes, Simon, any last words from yourself?
Yes, I would like to thank everyone to attend this webinar. We are very pleased you took the time with us today.
Wonderful. Well, thanks once again, guys. You've put a lot of hard work into preparing this presentation. It's very informative, very detailed, and we look forward to anyone who's viewed the webinar today to reach out to us with additional questions, and we'll be happy to help. Okay, so I think we're done for today. Thanks all for your time, and we'll bring this webinar to a close. Thank you.
Bye-bye.